A very decent good morning to all of you. I welcome you all on day 5 of the workshop. Today we'll be having two lectures and one tutorial. The first lecture will be from 10 a.m. to 11 a.m. Cellulosic ethanol and its potential applications, techniques and opportunities. Then we'll be having a break. The second lecture will be 11:30 to 12:30, cellular machinery for bioethanol production. Then we'll be having a break for the lunch. And then we'll be having the tutorial 5 from 2:30 to 4:30. It will be on conceptualization about novel techniques in cellulosic bioethanol production. And today we are honored to have Dr. Promila Batra with us. We welcome you now.
Just please, madam. We welcome her because she was the GIAN coordinator before the present coordinator before her. And she was very much instrumental in putting up the proposal, and we did in short time, because we got, I think, 1 month time to prepare everything, including getting consent from the experts and all that. And she helped a lot, and I think we had more than 10-15 meetings.
Yes.
So we completed all the formalities, and I request you to just say a few words.
Sure, thank you so much, Pratyush. Good morning, everyone. As Dr. Pratyush has already told you that I am the then coordinator, let me first of all express today about myself. Whatever you are doing today, that was my dream project. I'm very thankful to you. I want you to kindly give a standing ovation to them. Please come to the side. We had very less time. We had very less time. And if you had not said yes to this, we could have not been able to do it. Thank you so much. Thank you, friends. Now my thanks go to My thanks go to Pratyush. Definitely, along with all other those 7 colleagues of mine who have submitted projects. They really worked day and night for everything. Definitely, I was with them, but when it comes to academics, I was zero in that. They did it. I tried to read them. I tried to understand them so that I could develop a faith and confidence that whether or not we'd be able to get it. And they did it. I would really be happy if you can give a standing ovation to Pratyush. Please up here.
Thank you. Thank you.
My blessings to both of you will always remain. Please. I'm very happy because I'm much passionate about the Mother Institute. Not that I have only catered, see, wherever we work, not that we cater to that university or the organization. They both will agree that they also cater to us. This is a mutual relationship. So the nurturing depends upon both. We, the people who are working, the students and the authority. So that's how it has happened. Thank you very much for listening to me. I just came to listen to you once, and thank you for this gesture. Yes. Thank you so much.
I just wanted to update you and to others who are watching live that we have participants from industry as well.
Yes.
He is there. He is from pulp and paper industry.
Okay, great.
And this is first such course where industrial participants are taking.
Yeah, that's what we were looking at. Yeah. We aimed at it. And, so we kept a separate provision for that.
Yes, but he is a student also.
Okay.
Because he is a GIAN.
That doesn't matter.
Yeah. So
we should reach you.
Yes.
That's more important.
We have a participant from Sagar University.
Oh, great. Great.
And there are few student participants from here. We have a faculty also from our department.
That's
he is also participating.
That's
so it's very good going.
That's really good.
We have our colleagues. I request Dr. Rajiv Kapoor, Dr. Pooja Suneja, Dr. K.K. Sharma. They all helped me. Please come here. Thank you so much. So, because we don't have any validatory type of function in this program, so we introduce to others. They already know. Dr. Kapoor is there. Dr. Anita, please come. Dr. Suneja, and Dr. K.K. Sharma is also there, but he is scheduled to come. He is preparing some materials for the course.
Okay.
And she is Dr. Anita.
Hello. Yeah, we are taking care
of all the hospitality and all that.
Probably somewhere in ethical consideration.
Okay. Maybe some other.
Okay.
So,
I thought that I had
so there are
evaluated
other
one of
colleagues.
your
There are other colleagues. Then the scholars we have. Raki, she is one of the main scholar. She is entering all the.
She's holding.
Yeah. So
She's
we
holding.
are doing whatever is done because of their support. And I really thank all of them. And participants are also. She is Dr. Richa Aruna. She is faculty in lovely professional university.
So that's great.
Yeah.
So
and she is from Jharkhand.
Oh.
Yeah, one participant from Ghana. So we have diversity of students, but we were limited to 20. So we selected out of them. So 11 people are participating because few people they could not make it due to some reasons. So
but whatever it is,
yes.
I'm happy that whatever you are imparting to them, that's for the student lot, that is for the research scholar lot, that is for the faculty, and spread over the nation. So I'm sure that whatever are the applications and the benefits which these people are going to have, MDU is able to make it reach to the various parts of the nation too. So I congratulate my university also for that. It's a really great thing. I'm very happy. Thank you so much. I wish you all the best, lot of blessings. Keep it up, keep growing, keep laughing, keep growing, keep laughing, and keep smiling.
Yeah, and I just want to tell she's a professor of psychology.
That's why I said.
So that's why keep smiling, keep laughing, stay positive, all those.
Yes, remain decorative and keep smiling.
Yes.
That's what this
Thank you, ma'am.
Thank you.
Thank you. We will start. Yes, please do.
Good morning, everyone. Welcome to the lecture night. In this lecture, I will be very glad to share my information from my laboratories in Chinese industry with you. Some of them they achieved great success in the field of second generation bioethanol. However, in China nowadays, the most important biofuel is still the first generation bioethanol. I will introduce the first company to you. It is the China Oil and Foodstuffs Corporation. They call it GUFCO. GUFCO is very famous in the field of bioethanol. It is now the largest bioethanol supplier in China. It accounts for 40% of the bioethanol in the Chinese market. The largest factory, the largest plant for production of bioethanol from corn starch located in my hometown, Anhui Bengbu, my hometown. This is a picture. Anhui is a province. Bengbu is the city. The plant is located there. Yeah, Bengbu has another name, the Pure City. Pure City looks like a pearl in the necklace. Yes. Yes. And in this factory, we have a very huge productivity of bioethanol. For each year, there are 0.32 million tons absolute ethanol for used for the biofuel purpose. And it collaborates with Silica to produce commercially used gasoline blended with 10% ethanol. This company is the most successful.
Yeah, this I just want to tell to the participant. This 15 million RMB, that is the Chinese currency. Okay, so 1 RMB is equal to 11 rupees. Okay, and dollar also you can exchange accordingly. So 15 million RMB.
With China started the program of bioethanol very early, 15 years ago, in the year 2003.
This is first generation raw material.
First generation, yes.
No, RMB, I think it is a different currency. Okay. This one?
Yeah, Chinese yuan.
Chinese.
Yeah, Chinese yuan. Next company is GIAN, located in Henan province. This is another very large biorefinery.
Biorefinery?
Yeah, biorefinery. At night, yeah, lights.
Okay.
The is used for the distillation of ethanol after the fermentation. Their product focuses on the fuels used for the vehicles, for the cars and trucks. The starting material is starch, mainly is corn starch, and there are a lot of process steps, and finally all of the treated materials enter the fermentation tank, and the starch sugars and converted to ethanol there, and finally we made into the absolute ethanol through an evaporation process and another process to remove the residual water. It's based on some molecular cellular process. This is a picture of the third company, Longli, located in Shandong province. This is a real second generation biorefinery. Previously, Longli, this company, they produce sulfur and oligosaccharides as their major product from the corn residues. During the production, there are a lot of large amount of biomass, cellulosic biomass, and xylene biomass as residues. They cannot burn it at all. So they tried to develop a new technology in order to process, to deal with all of the solid wastes. So they use enzyme. There is an enzyme cellulose mainly from supplied by University of Shandong. University of Shandong, there is a dedicated laboratory of microbiology. In that specific laboratory, they preserve a very good strain. It is a penicillin strain. It produces active cellulase of high activity, comparable at a comparable level to the Genenco product or to the Novozymes product. It's a very good product. Because that process starts from the corn stover. From corn stover, first xylose is extracted. It's extracted to produce food additives and feed additives. There is also some products derived from xylose, like the xylitol and arachidose. Arachidose is another chemicals derived from corn stover. The values enriched with cellulose, enriched with the hectose and the lignin. They will convert it finally to ethanol. Use a second generation biorefinery. The ethanol blended with gasoline to be a fuel, and the lignin finally to be used as a polymer material. I don't know if they have the lignin polymer product, but they do produce ethanol from the cellulosic residues.
Which culture they are using? Saccharomyces?
Yeah, saccharomyces, yes. But I believe that they use engineered saccharomyces. I do not have the information. It's a commercial secret.
Oh, commercial secret.
All of these have been published in the website. This company located in Guangzhou, in my city, in Guangzhou, and this city was established by 2 undergraduate students from my school.
Great.
Is that very young? Yeah.
That's it. This
Yingsheng.
okay.
Yingsheng. They founded this company maybe 10 years ago, but this year, 3 years ago, they achieved success, and they got a very highly developed technology, overall technology, to convert bamboo and sugarcane bagasse, okay, through a low temperature treatment. Because for most temperature, for most pretreatment processes, sometimes there should be a digester, such as vertical, such as spherical. I showed you in the past lectures. And during this process, there is a high temperature, for example, over 150 degrees centigrade as a pressure. But if the biorefinery is built up in a place nearby a city, these facilities may be not safe. So a low temperature process is highly desired. This technology was provided by a professor in my school, in my department, Professor Oliver. He is also the supervisor of the course when they are in the school. This process highly depends on the reaction of acetic acid with xylose. With xylose, finally xylene will converted to xylo-oligosaccharides, and some of them tend to be sulfur and tend to be mono sugar. I introduced a microwave that can convert not only sugars but also the acetic ion. Almost all of the acetic ions and ions finally can be converted by the microbiome. It is the cell made of cell but full of other fillers. Finally, we get a fertilizer, yes. And the residual lignin from the pretreatment, the organism lignin. Organism lignin I introduced you, we can derive a lot of different products from the organism lignin. For example, the lignin carbon fiber. Yeah, lignin carbon fiber. After the combusted in the furnace of high temperature, all of the lignin tend to be carbon, but the carbon content is usually around 60 to 70%. It has a very high, a very good, thermostatic properties. And the sugars can also be converted to bacterial cellulose. We discussed it in past lectures. All of these products, the development of these products were achieved in the state of Rohtak and field engineering in our dedicated lab. The next company is China New Energy. China New Energy is very famous. It's one of the most important factory builder and equipment supplier in China. In the field of biofuel energy in China. Yes. It's my honor. My first funding from the industry.
China New Energy.
Provided by China New Energy. Very important for me because at that time I'm very poor. My salary level is low, very low. Yes. They supported me for 2 years. Very important. Nowadays, in the past decades, they built up a lot of biorefinery facilities for not only bioethanol but also biobutanol. Their biobutanol factory facilities accounts for 30% in the world.
Okay. Sorry to just. This is 1 lakh.
Yeah, it's ethanol. Yeah, from corn, yes. The first generation.
And from cassava.
From cassava, yes.
Okay.
This cassava starch is mainly used for industrial purpose, like for paper coating. So, and in China and in Southeast, there are a large amount of cassava area. So, there is investment to use cassava. Not only in China but also in Thailand. They want to convert the starch into ethanol fuel. And these facilities were built up in one in Thailand, another in Indonesia. As I mentioned in Indonesia, sometimes I have a friend from India, and maybe I lead into a hotel in China. They cannot disintegrate the Indonesia and the India. They ask me, is India Indonesia? They always ask me this question. And this facility is for bioethanol, and it's also located in my hometown, Anhui. This one is for production of acetic acid. So acetic acid from corn depends on the fermentation capacity of some special bacteria. Next, let me introduce some integrated biorefinery. Integrated biorefinery means it is not a sole biorefinery. It combines with other industry. For example, with the food industry, with the pulp and paper industry, especially pulp and paper industry, because for second generation biorefinery, the starting material is usually lignocellulose. Lignocellulose is also the material to make a pulp, to make paper, to make paper powder. So there is a competition between the two industries. To solve this problem, a very famous US professor, Professor Hannigan, he provided a new concept many years ago. The concept is integrated forest biorefinery. This concept is like this. In the pulp and the paper process, all of the lignin should be removed. Most of the hemicellulose should be removed. Finally, cellulose is enriched as a white fiber. So we do not use lignin because lignin in pulp mill is mainly for the generation of energy, but we can utilize the hemicellulose. If we pre-extract hemicellulose from the wood chips, from other materials, we can utilize it. And after the pre-extraction of hemicellulose, during the subsequent pulping process, the consumption of chemicals is also lowered, decreased, because hemicellulose also consumes alkaline, like sodium hydroxide, sodium sulfide, because it reacts. So this concept has widely been applied, extensively been researched in China. We developed a lot of technology in order to isolate hemicellulose from wood chips, and then do the pulping, do the craft pulping, do the bleaching. We have a lot of technologies, including the hot water extraction, dilute alkaline extraction, and the dilute acetic extraction. Acetic acid extraction is now fully utilized, especially for the production of dissolved wood pulp. Am I right? Yes. For the dissolving wood pulp is a very pure cellulose, very pure, as a substitute of cotton fiber. Yeah, because there might be some shortage of cotton fiber. If once there is a war, once there is a water war, the cotton fiber is very important material. So, and sometimes the cotton fiber price goes very high. So it is important to develop alternative technology to produce almost the pure cellulose from the cheap material. In southwest China, most pulp mills, they use bamboo as a material to produce the dissolving wood pulp or wood pulp. They use sometimes they use the technology of hemicellulose extraction. So this concept is very reasonable. It has been applied in the pulp mill. But the major product from hemicellulose is mainly sugar. Okay. So there's a long conversion process for all of the components. Another concept was initiated in my lab. I developed this technology. I use cell separation technology, cell separation strategy. I found that there are a large amount of trees like this. It's a palm tree. In South China, in Hainan Island, in Southeast, maybe in Middle America, this material is very abundant. And the leaf, see, this is a leaf. The leaf is very long. It is usually 6 to 8 meters, and the dry mass 1 to 2 kilograms for one leaf. And there is a typhoon. A lot of leaves fell down. Okay, so we can easily collect them, and the biomass is intensive. And in South China, there are 0.2 to 0.3 million trees, million number of trees growing per year. And if we are going to utilize the leaf from palm tree, we can only use the fiber for pulping because all of the paper is made of fiber, not from the parenchyma. Parenchyma is not fiber. Although their major components are similar, made of lignocellulose, but their size dimension are totally different. Okay. This is SEM of palm tree I'm created in my lab, and we can easily get the this is a vascular bundle. This is a vascular bundle. Okay, has a high density, and these cells are parenchyma cells. Parenchyma cells is usually mainly for the storage of nutrients. Is for the transport of water. Yes. If we break down the cell wall structure, we can get the separated the fibers, separate the cells. This is fiber, vascular fiber, and these are all parenchymers. So I developed a technology to divide them. There are a lot of other species like royal palm, like oil palm. Oil palm is very important in Indonesia and Malaysia because it produces palm oil. Palm oil is very abundant. Yeah, it's of high demand every year. And in oil palm trunk, the parenchyma has a very high demand, very high ratio, around 60%. And for wheat straw, for sugarcane acid, always also has a high ratio of parenchyma. So it's a very good source because in pulp mill they do not use this material. I developed this process 5 years ago. First, I use a semi-chemical cooking. Semi-chemical cooking is not a full cooking. A full cooking, over 90% of the lignin should be removed, but a semi-chemical cooking, at most 30% of lignin is removed. Okay. So I will obtain spent liquor and cooked solid. Cooked solid is then fractionated to fiber bundles and parenchymers. Use a lot of different equipment. This one is for cooking, for digestion. It's a digester. This one is for cell division, for cell separation. Depends on different size of the screen in each step. And finally, I use another equipment. It is for refining of a fiber bundle to separate the fibers from a bundle, so that it can be used for paper making. This is the bundle before the refining. This is a refined fiber. Only this one can be used. Okay, after the cell separation, you can see that this is the fiber bundle. This is the ratio of parenchyma. Very few middle parenchyma. Very few. So they can be easily separated with each other. Then the pulp fiber is bleached and to make the paper product. And parenchyma is enters SSF process to make ethanol. Yes. Spent liquor can also be recovered most of the simple sugars can be converted to ethanol, but I do not do this this experiment. These are samples obtained from the process. This is chips from the palm front. Yes. After that, this is a fiber bundle. This is the parenchyma. Parenchyma, they are very small, very tiny particles associated together. Okay. We also found that for a fiber and the parenchyma, they have a totally different digestibility. Parenchyma, because of its cell, is very small, and almost all of the surface covered by cellulose. But for a fiber, on the surface, mostly covered by lignin. So cellulose has a higher accessibility to parenchyma, not only because of the size, but also because of the surface. Okay. So at a very small cellulose loading, around 10 FPU by mass, over 90% of the cellulose can be converted to fermentable sugar. But for a fiber, it is not easy, very difficult. We also tested the silica body. During the process, see, we have the last one. We have last screen. From the last screen, most of the silica removed along with the effluent. And for the quality of the pulp derived from the process, it is very good. After the cell fractionation, we tested the filtration capacity. Because the paper making process is a filtration process. We have a screen. The screen has a hose, and all of the fibers and other solids they deposit on the surface of the screen. If the hose is filled by the parenchyma, the screen filtration rate is lower. We pursue a high filtration rate. So after the fractionation, the drainage of the material on the paper in the paper machine model, we have a model simulating the paper machine process. Okay. The drainage property is highly improved. And finally, we claim that this process is reasonable. It is still developing. I will publish a new paper, but not already. The third part, I will introduce some biorefining efforts I made in Hong Kong with Professor Liu Shaoyuan in Hong Kong Polytechnic University and Professor Carol Lang. Carol Lang is a very famous professor in Hong Kong, working in the field of biorefining. We tried a lot of different materials. First, the turf grass. Turf grass is a waste grass cut from a football ground. Okay. We have a lot of grass ground in Guangzhou, in Shenzhen. Some ground is for golf. Yeah. And every day there is grass waste produced from the ground. Thousands of tons, and because of the grass is specific, is particular. Okay, it consumes a lot of chemicals for the nutrients and to kill the insects and to keep its growth healthy. So, absorbed on the grass waste, there are a lot of chemicals, toxic chemicals. It cannot be a landfill because it contaminates the soil, contaminates the water. And it is also not good to burn it because it has a high ratio of nitrogen, high ratio of sulfur. Yeah. So we developed a lot of technology to utilize the turf grass. Not only turf grass, but also the Christmas tree. discussed it with you in the last lecture, and something like this waste from the express package, it is now allowed. And from the waste clothes, textile waste. Textile waste is sometimes not easy to handle it because it contains not only cellulose but also the chemical polymers. And the content, the issue between natural fiber and chemical fiber varies from different sources. So we spend a lot of time to study how to deal with, how to manage this waste. This picture is from this year, January this year. Our government published a new policy that no foreign waste can enter China. We have a ban. Previously, all of the waste from US, from Europe, first they arrived at Hong Kong and then transported to mainland China. This picture is a waste plastic bottles. This worker is handling with all of these wastes to select the metal, or other materials from the plastics in order for the recovery of the plastics. It's a good work. It provides a lot of job actually. However, these wastes are very dangerous, especially for human health. My mother's mother died from cancer because she worked in a plastic waste company for 10 years and she died from cancer. I think mainly because of the toxic substance or other contaminants in the plastic waste. So our government banned all the waste not clean. Okay, and all of Chinese people we support this policy. Although the starting material rises, the price of the material of the waste material, the price is higher, but we support this policy.
So I just want to ask you whether you were getting the waste material from other countries also.
Yeah,
they were sending through ship.
Yeah, nowadays we use waste material only from China. We use only
and it is recyclable.
It is recyclable, yes. Such as the plastic bottles, we use a thermal process, mix the plastic PE with wood powder.
Okay.
And make the wood board, like wood board.
Okay,
it's a complete board, yes.
And also, you got some stuff from US also. US was also sending.
Previously, we import a lot of waste paper, waste plastic, waste clothes from US.
Okay.
But now banned.
Now banned. Okay.
The waste paper should be like the waste older newspaper, older office paper, should be processed in US. Make it as a paper board to remove all the contaminants, all the polluted substances. Then we can import it. We import only the product, the paper product, not the waste. In the biorefinery of urban, for the sustainable waste management, we established a joint research group in many universities in Hong Kong. I provided the pretreatment technology for them, only pretreatment. I use a refrigerator. It is a freezer. It has a temperature negative 20 degrees centigrade. I use a method developed by Professor Zhang in China. She developed the technology use chemicals. The chemicals include sodium hydroxide and urea. These two chemicals combine with each other at a very low temperature, we dissolve cellulose very efficiently. Break down almost all of the cellulose crystal structure. And after regeneration with phosphoric acid, but sometimes I use water not instead of the phosphoric, because phosphoric also pollutes the river. Yeah. It causes the overgrowth of algae. Sometimes I use water to regenerate the cellulose from the solution, and I can easily separate the cellulose from the waste textile, waste clothes. This is a microscopic picture. I obtained from the regenerated. This is a regenerated cellulose from this process, from the waste clothes.
This process was for clothes.
Okay, this clothes material is from lab coat. And yeah, and we also use half cotton, half chemical fiber with clothes. All of them we purchase the material from Singapore. There is a waste management company that supplied us these materials. Yes. The next process is enzymatic hydrolysis. In addition to enzymatic hydrolysis, Professor Carol Lee, they developed a technology from use fungi, use Aspergillus niger, and maybe Trichoderma resin to produce cellulose from in order for the hydrolysis. Okay. And the hydrolysis is performed in Hong Kong Polytechnic University by my friend Professor Liu Shaoyan. We obtain the sugar from the conversion of cellulose. It's not difficult because most cellulose in textile waste is almost pure cellulose. And the residues, PET residues, synthetic fiber is residual because no enzyme can digest it. And it's residual and recovered by a respinning. It's a thermal process. It can be reused as a chemical fiber. This process is sustainable. I think it's sustainable. Although the cost for the treatment cost for the overall process is still high, but it is sustainable. And it is in this year we obtained about this scheme obtained invention. It is a golden medal. Awarded a golden medal in Geneva invention exhibition. I think it's a very good award. Yeah. However, my name was not listed. There. But Professor Caroline wrote me an email and sent me for my treatment work. This is her email.
So we congratulate Dr. Liu. It's a very good.
Okay, I leave a question. This question is: are there other primers feedstocks that have a high ratio of tranchyma? If we have a feedstock like this, we can do the integration part and the biorefining process. I give some pictures. The first picture, you are very familiar with this. This plant is banana. Yeah. This plant is pineapple. Yeah, I added pineapple in the Indian market, local market. Very big. Bigger than what I found in Guangdong. We tried to use this biomass in my own lab. This one we published this paper many years ago. We found that the parenchyma, the non-fiber components, totally different from other plants. Because the banana tissue is very special. It preserves a large amount of water in its stem, a very large amount.
Banana t-shirt.
Yeah, if we cut off a stem of banana.
Okay.
Okay, like this.
Okay.
And then the water.
But
General like this. Yeah. Like
so,
temperature.
in China, banana t-shirts are
Not used now. Not used now. We do some research, but not very successful.
okay.
We always fail. A lot of failure, yeah.
Okay.
And for the pineapple, we also failed. And because when I do the integrated pulping and biorefining, I found that there are a lot of aromatic cell, the cell on the surface of here. It is full of pectin. And the pectin is sticky, is viscous and sticky. Combine all of the fibers together. I cannot separate them. I cannot separate them through a screen method. So nowadays I'm trying to use pectinase combined with cellulase and xylanase to treat this material. And finally I'm successful to get a paper like this. This paper is made from the leaf of pineapple. Yes. The things are not too bad.
This must be a leaf, or this is the leaf.
This one? This one. Yeah.
The paper.
Yeah. The pectin content is very high. If we are going to use this material, we have to remove pectin. We can use a microbiome, but I do not have good results with that. Yes. Have a question? This work is highly supported by my school. One professor, Professor Chen Gang, working with me. He has 4 students working in my lab, and we do the enzymatic treatment and we do the paper making together. If this process is successful, now we can use it to replace the waste paper, with the old paper from US, because there is a shortage about the shortage of the waste paper now because of the ban policy. I will show you 2 more pictures. This picture is a award certificate of my undergraduate student, one of my undergraduate students, Mr. Li. Mr. Li helped me a lot. He entered my laboratory, my lab, since 2 years. The 2nd year, he entered the lab and worked for me. Developed a lot of technologies. This one developed by him. He helped me to optimize the combinations of different enzymes for the treatment of biomass. And in this, in his dissertation paper, he helped me to study the oxidation of glucose through a glucoside glucose oxidase way, and aromatic oxidation of glucose. And we found that if we use this enzyme to convert the cellulose, the conversion ratio is usually 70%, not 100%. And if we are pursuing 100%, it usually costs a long time. We don't know why. With the help of Dr. Puneet and Dr. Ravi, we use autodoc process, and we found that glucose, there are 2 forms. Okay, one form is D.
L form.
Yeah. And it has another form, right? L form. D and L. Yes. The position of hydroxyl group is different at the different positions. If we use a computer to simulate this process, we found that the binder is the ligand of glucose different form. The binder with the active sites of this enzyme differently at different sites. We explained it like this, and we also planned that all of the L glucose can be slowly converted to D glucose. So finally, 100% conversion ratio is achieved, but not easy. passive time. This work is accomplished by another undergraduate student, Ms. Zheng. Ms. Zheng helped me to isolate fungus, celluloid fungus from poor tea. Poor tea is very similar with the black tea in India. It's commonly consumed in China. In the poor tea, the tea leaves is fermented by a specific microbes for a long time. So this microbes can produce at least definitely can produce cellulose, the cellulase. Not only cellulase but other enzymes that can tolerate the phenolic compounds, because in the tea leaves there's abundant ratio of phenolic compounds. So I do this work like this. Ms. Zheng helped me to isolate a fungus, and we get a hydrolysis. This is a culture. We also identified it, characterized it with a 16S DNA technique. Finally, we use this one to do the direct ethanol production from waste paper. We obtained a cellulose production like this, 4.8 FPU per milliliter. It's not high, but it's okay. However, the ethanol accumulation is very low, lower than 1%. Probably because this fungus has a poor ethanol tolerance. This work has not been published well. We are still working on it. Thank you. Thank you for
this. Just go back. So this you didn't publish, but the technology is available with you.
Yeah, not published yet.
Okay.
I do not have sufficient time to.
No, I'm really very happy to see a lot of developments, especially from the waste materials.
Yes,
So Christmas tree, you have just show me that slide. I just want the students to see that. Go back. The Christmas tree. Christmas tree. Yes. Yeah, this one. This slide gives a lot of ideas about the projects. Like you can initiate small projects, especially. So like you have a lot of this waste, packing waste.
Christmas tree. This idea initiated by Professor Yusori, my friend.
Yes, yes. And this also waste process. Yes. So this bioprocessing of these waste cloths.
Yes.
Do you have the plants for processing it?
No, we do not have plants. We have only a lab scale.
Lab scale, okay.
Yeah, we are trying to establish a pilot scale.
Okay.
Now, Professor Liu Shaoyuan in Hong Kong has purchased some equipment, but
Okay.
not ready.
Not ready.
Not ready, yes.
And this also waste express package.
Yes.
We get a lot of waste package.
Yeah, waste packaging cannot be utilized because there are a lot of glues, plastic glues.
And this Christmas, the most wasteful time of the year, the garden.
The garden is.
So normally these Christmas trees, what they are doing, they are throwing to some places.
No.
Once the function is over, Christmas is over.
Landfill.
Landfill.
Yeah, in Europe they were cut it into pieces.
Cut it into pieces. In
But
Europe.
In Hong Kong, in US, mostly.
This is Hong Kong picture, China. This is a China picture.
Yeah.
Okay. So it's really waste. It's not a waste. Yes, it's a wealth. So you have so many things to do. And I think especially in labs we have a lot of these type of waste materials, cardboard waste. You can use it for this. And this banana, it was not successful.
Yeah.
You got the patent of this technology.
Banana
Banana
of banana.
You
to,
have
to tell the difference between banana and the other plants in South China.
no. I am just telling that whether we have some patented technology for t-shirts.
I have a very good idea to develop new papers from new materials.
So
Like
we will work along with Maharishi Dayanand University. We can try such things.
I have a very small program for undergraduate students.
Okay.
Yeah, in my school, undergraduate students are can usually get financial support from my school to take part in the experimental work. One idea I provided to them is mushroom waste. I introduced here mushroom waste because we cut is the best part of mushroom after harvest, but we use residues. Use the residues, almost a pure mushroom fruit body. It's full of fibers, but not the cellulose fibers. It's another kind of fiber.
Yeah, I have seen their plant for students and other participants. They are using the waste cotton because in blankets and all that, when they are getting older, we normally throw the blanket. So they are taking those cottons. Like sometimes we also reuse it in filling it. They are using it as a material for mushroom production. I saw a plant where all these waste cotton as a material is used for mushroom. And I don't know, it's a small plant you have showed me. I think in the province, your province. Small plants. And they are producing a lot of mushrooms. And mushroom is very delicious for Chinese people. They are like
this GIAN has acquired a patent, Chinese patent, to make a paper from mushroom, but it's transparent, like plastic.
Okay, like a plastic, but eco-friendly.
We obtained a patent number from China. We also published the paper from it.
Okay. We are very happy. Participants, if they have any discussion, anything you want to have, we have 2 minutes. We have 4 minutes left in this session. 4 minutes one.
4 minutes.
Yeah. You can.
So we have very nicely discussed about the palm tree, which is fractionated into fiber and parenchyma,
Yes.
where fiber can be utilized in paper industry.
Yes.
And from parenchyma we can generate fuel.
Yes.
So what is the composition of this parenchyma cell? Lignin is also there, or what is the full composition?
Yes. So their chemical composition. This is a fiber. This is parenchyma. Parenchyma very small. The chemical composition, major composition is cell.
Same.
Yeah.
Cellulose, hemicellulose.
Cellulose, hemicellulose, and extractives and lignin. But the silica content is different. Okay. Silica content is different.
Is it more or less?
And the ratio of the lignin in this part is small particles, parenchyma, lower than fiber.
So you have tried all these species.
Yes.
Wheat straw, sugarcane, oil palm.
In my training, my professional training starts from the recognition of different plant tissues.
Okay.
The flower from the plant.
Because in our India, in South India, Kerala and all that, we have lot of these palm trees. And we also have banana. Lots of banana trees. So, but normally I see we are using it as a plate, small plate. We are making plates and for food. So, like you know.
How could you separate the fiber from the banana? You said that you developed the technique. The separation of the parenchyma from the fiber. First you pulped it.
Yeah, I published. Previously, there are some other publications. But for this purpose, for the integrated pulping and bulk farming, I think it is first.
You published in bioresource, I think, bioresource technology.
Yeah, bioresource technology.
Yes. I remember. A very good paper.
No, I was talking about how it is sorted out, like fiber, how the fiber was separated from the.
I will use the machine. The machine like this. There is a mesh screen, a large hole. And there is a smaller size screen, smaller hole. All of the materials flow step by step. Different size can be separated easily.
So, Rakhi, I think we are now. Can close the session.
So with this, we come to the end of first technical session. Now we'll be having a tea break for 30 minutes, and I think we will be having a group photograph during this time. So we shall all proceed for tea. Thank you.
Thank you very much. Thank you very much.